All right, so here we go. Approximate 3.01 to the fifth. Determine if the linearization approximation is over or under. So in this case, I'm not quite sure what it is, but we can call the function x to the fifth, and then we can choose as our center, I'm going to call the center C, of approximation to be what? What's the closest number to 3.01 that you actually know the value of to the fifth power? 3. Yeah, very good. Now notice this one is only 100th away from 3, whereas the two we did previously, one was a full unit away, and the first one was like a full 6 units away. We were really, really close this time, so this should be good. It should be a good approximation, but it also depends upon the severity of the curve, which we'll analyze that here at the end. So now I'm going to write the equation of the tangent line for the function x to the fifth at 3. So the point is going to be 3 comma 3 to the fifth. 3 to the fifth is 243. You can get that pretty easily. F prime of x is 5x to the fourth. So if you plug in your 3, f prime of 3 is going to be 5 times 3 to the fourth, which is 81. That turns out to be 405. Now, unlike the other functions that were really, really flat at the point of tangency, this one is, well, not really flat. This one is super duper steep. So when your curve is flat, let's just kind of look at it. When your curve is flat, your tangent line is going to hover close to the curve for a much larger radius than it would if your graph was like super steep, right? Notice if your graph is super steep, your tangent line, as you go the same distance away, already starts deviating from the actual function. And so x to the fifth is a pretty steep curve. So luckily, we're not that far away, 100th of a unit away. All right, so let's go ahead and write the equation. We have enough. Call the equation now L of x because it's the line. And you get the y value of 243 plus the slope of 405 times x minus 3. And now the notation starts, all right? The function value at 3.01 is approximated by the linear function at 3.01. So that would earn a check just by itself. And then that equals, if you plug it into the Taylor form, it's ready to go. You get 243 plus 405 times 0.1 or 0.01. Now multiplying by 0.01 is the same as dividing by 100, and then dividing by 100 is the same as just moving the decimal places 2 to the left. So you get 4.05. So if you add those together, you get 247.05. So that's what 3.01 to the fifth is approximately. Now, is that too big or too small? Let's see. We got to find the second derivative. The second derivative is 20x to the third power, which because we're working from 3 to 3.01, we'll just say that this is positive for all x greater than 0, right? So that covers the interval we're working in. Everything to the right of 0. So if the graph then is concave up, our tangent lines are below. So now you'd say, so L of 3.01 under approximates. That's a long word. Under approximates f of 3.01. In other words, the actual value is a little bit bigger than that. Now let's see how much bigger. We have the luxury now at the calculator. We came up with 247.05. 3 to the 0.01 to the fifth is 247.07. So notice I was only 100th unit away from the center, the point of tangency, and I was already 200ths off. But still a pretty good approximation. Pretty good approximation. All right, any questions on example 3? Yes? No? No, no questions. Okay. All right, let's do this last one, then I'll kind of shift gears here a little bit. Approximate the natural log of e to the 10th plus 5. Determine if it's an over or an under. So we'll do this one together very, very quickly. What is the function going to be? Natural log of e to the x plus 5? Oh, that could be. That could be, but that's going to be a little bit harder to take the derivative of. We can make it work like that. I'm just going to use the natural log of x, yeah. This then, I'm looking for f of e to the 10th plus 5. So what is the closest number to e to the 10th plus 5 for which you know the actual value of the natural log? 1. E to the 10th, right, e to the 10th. So it's kind of set up for you to kind of almost trip over it. We're going to center it at e to the 10th. So you can write it like that, C for center. We're centering our approximation at e to the 10th. So we need the point. The point is going to be e to the 10th, comma, what is the natural log of e to the 10th? 10, good. The derivative is 1 over x, so the derivative at e to the 10th is 1 over e to the 10th, or e to the negative 10th, if you want to write it like that. So the linearization, the tangent line equation, same thing, in Taylor form is the y value of 10 plus e to the negative 10th times x minus e to the 10th. And now we'll plug in. So we'll say f of e to the 10th plus 5, we're 5 units away here, is approximated by L of e to the 10th plus 5, which actually equals 10 plus e to the negative 10th. Now if you plug e to the 10th plus 5 in for x, the e to the 10ths are going to cancel and you're just left with 5. So this ends up equaling 10 plus 5 over e to the 10th. And right there, we're kind of done. We're kind of done. You can actually approximate that somewhat by knowing that e is approximately around 3. So that'll give you an idea. But the point at this time is not to actually compare the values, but just to make sure that we have the mechanics down of how to do something like this. Now, is it an over or an under approximation? We can answer that pretty quickly. Natural log of x is always concave down, right? So if you don't want to find the second derivative, you could say this. Since f of x equals the natural log of x is concave down, instead of saying the second derivative, finding it and saying it's negative, is concave down for all x greater than 0, f of e to the 10th plus 5, thank you. What do we say, over or under approximates? Over, yeah, because it's concave down, the tangent lines are above. Over approximates. What's that? Let me catch up with y'all. Oh, for all greater than 0. I'm still not seeing what's... The function is ln of x. It's concave down everywhere to the right of 0. So f of e to the 10th plus 5, that's not fine? Oh, okay, yeah. How about, I'll change it. F of that is over approximated. There you go. Y'all are right. I'm sorry. I'm trying to read this little piece of paper that I got. So I have a good excuse. Hang on. Is over approximated by, you know what? I don't like that. That's the passive voice. That's what it looks like, right? L of e to the 10th plus 5, thank you, over approximates f of e to the 10th plus 5. Good. Y'all are so good, y'all catch little subtle things like that. Other classes would be like, okay. All right, so good. Way to go, guys. Oh, and this is for you. I'm done reading it. All right, any questions on linearization? Y'all's are going to be a little bit easier. Y'all are going to be handed the function, and it'll say here, approximate something at this value of x. And so you'll be handed the center. The ones we just did, where we had to get our own function and find our own center. That's going to be handed to you. You're going to know what to do. All right, let's take a look at this picture. Up to now, dy dx has just been another way to write f prime or y prime. It was nice because it's Leibniz notation, and we like always kind of rooting for the underdog. But it was also nice because it preserves the slopey feel, the division feel of slope, right? Slope is a division, it's a quotient. Now the difference between delta y over delta x, remember this is your finite slope. This is your algebra slope, the difference quotient. I'm having a hard time writing that. This is your algebra slope. So what delta y is, it's the change in two y values. Delta y and delta x are both finite and measurable. But because of the limit, remember the limit forces the 2 points that we're using for the difference quotient to be so close together that you can't tell them apart, dy and dx are infinitely small and immeasurable. Immeasurable on the curve. On the curve. Still can't write. Still can't write. There we go. They're infinitely small. They're ghosts of departed quantities, as Leibniz actually called them. Pretty neat. But we also know, and this is worth noting again, that dy dx itself, when you take the quotient of those two infinitely small, immeasurable quantities, you get the slope of the tangent line. Okay, but at that point, the difference between the two at that point is immeasurable. But it does end up being nicely the slope of the entire tangent line. So what this picture right here does is it kind of shows you the difference between delta x and dx and delta y and dy. So we have this function f of x. I'll highlight it right here in green. And if we're finding the slope of the tangent line at this x value, there is the tangent slope. So the slope of this line is dy dx. So if you want to get from this point P to another point that's delta x, we called it h back in the day, that's h units away, you're going to go up dy and right dx, right? That's the slope. If dy dx is the slope of the tangent line, from this point here to this point here, you're going to go up dy, and that's shown right here, and you're going to go right dx. So that's what dy dx is. dy is the distance then from the other point on the tangent line to the y value that you started with, and dx could be anything. In this case, delta x is equal to dx. So if we transfer this over by the same amount on the curve instead of on the line, if we go to the right the same amount and then go up and hit the curve, this right here, the difference between where we actually are and where we actually were vertically is delta y. So delta y essentially is the distance between the actual value and the original value, and the differential y is the difference between the tangent line value and the original value, y value we were at. And so this right here is essentially the error, right? The difference between dy and delta y is the error. Now, for small values, let me write that. dy approximates delta y, right? For small values, dy approximates delta y. And that's the whole idea behind the linearization that we did. As long as we stayed relatively close to the point of tangency, we can use the tangent line's value to approximate the function line value. So dy and dx by themselves, these are called the differentials. All right, so there it is. dy is called the differential of y, dx is called the differential of x. Now, here's a nice little use. We can treat this as an equation. And since dy and dx now we know can be treated as individual quantities, just like delta y and delta x, we can actually multiply both sides by dx, and we end up with this equation, which we'll see again later when we learn integration. So dy equals f prime times dx. The differential of y is equal to the function f prime times the differential of x. This is called differential form of the derivative. The differential form of the derivative. Instead of dy dx, which is just known as the derivative, this is the differential form of the derivative. We can use it to answer questions like this. Example 5. Find the derivative of each of the function in differential form for each of the following. All right, so we have a dependent variable of y and an independent variable of t. Normally we would say dy dt equals, but in this case I'm just going to say, well, let's do that. Let's do that first. Let's do it the old way, dy dt. It's going to be 6t squared plus 10t minus 3. There's the derivative. If we want it in differential form, here's what it would look like. dy would equal parentheses 6t squared plus 10t minus 3 dt. So it almost looks like implicit differentiation at that point. Take the derivative of y, get dy. Take the derivative of the left in terms of t, and then multiply by the chain rule dt. It kind of has that feel to it. But it's equivalent. The dy dt is not a single quantity. They can be separated, the numerator and the denominator. All right, z, with respect to x. Let's go straight to the differential form this time. On the left, we get dz, the differential of z, is equal to, now we have the what rule on the right? Product. So that's going to be 3x squared times the second goes along for the ride, plus x cubed times cosine of 3x times another 3. And now I need to multiply that by dx. And if I leave it like that, I'm not quite there. Very good. You need parentheses around the whole thing because it's a quantity and it has to be multiplied by the entire thing. What we're going to do later on is once it's in differential form, we're actually going to take the integral of both sides with respect to the indicated variable. So this differential form will come back later. Right now we're just practicing taking the derivative with this new notation. And the last one here, the derivative of the left in differential form is dm. On the right we get e to the blob, e to the 5q squared plus 1 times the chain rule, what? You're welcome. What? You're welcome. What? Yeah. dq. There you go. There you go. Differential form. Hardy har har. All right. So far, so good. We don't need parentheses, but it's okay to have them, right? But because it was still one term, it's better to have them and not need them than need them and not have them, right? Like a DQ blizzard. All right. I didn't need one, but I have one. Actually, I have two, and they're both extra large, so I guess I got to eat them. All right. Here's a nice application of differentials I think you will recognize. I hope you'll recognize it. This is what we just said. If delta x is small, for very small values, for very small delta x values, delta y is approximately the differential of y. That's what we did with the linear approximations. Okay. Example 6. A machined spherical bearing was measured with a caliper. All right? So you have a company, you make round bearings, and they need to be within a certain tolerance to be acceptable. So you can measure them with a caliper, which measures the girth, the diameter, and the bearing's radius was found to be 2.3 inches. Okay, 2.3 inches. With a possible error no greater than 0.0001 inches. So that's your margin of error. Your margin of error is 0.0001. So this thing, like if it was on a production line, as they're producing these, let's say they all had to be 2.3 inches, they're measured. If they differ by only, what is that, 10,000? Then they can make it. If they fall outside that tolerance, they're off the assembly line, and the workers have to eat them. Okay. What's the maximum possible error in the volume of the sphere if we use this measurement for the radius? What's the maximum possible error? So this is the type of question, when you're trying to find max possible error, this is where the differential would be nice. Because remember, the maximum error is, at the worst case, using the derivative. All right, so here's how we would do it. First of all, we need to find an equation for the volume in terms of the radius for this spherical ball. 4/3 pi r cubed, right. So if we take the derivative in differential form, we get dv equals 4 pi r squared dr. dv is the differential of volume. dr is the differential of the radius. Okay? So now, what's the maximum possible error? If this is 0.01, oops, didn't write with the highlighter. And the radius was 2.3. So guess what we can label this as? We can label the radius as 2.3, and this 0.0001, we can actually label that as dr. Yeah, very good. That's the maximum allowable tolerance. So we can let that equal dr. That would be this upper bound right here on the graph. And so now we could plug in. So dV would be the maximal allowable tolerance on the volume, and you just plug in. You get 4 pi times r squared, which is 2.3 squared, times dr, which is 0.0001. And that would be cubic inches. So since we have a calculator right here, or I do, I'll go ahead and type that in just to see what it comes out to be. 4 pi times 2.3 squared times 0.1231, enter. So the maximum allowable error for the volume would be 0.006647. So if that was your tolerance that you would accept, then you would accept the variation in the volume of each of these moles to be maximum 0.000 or 006647, the lesser known British spy agent. Well, you can truncate or round. You can always go more than 3 decimals, just an FYI, but they have to be correct decimal places. You can't just say, oh, it's 0.006, then I'm just going to put more like 782. If it's ever more accurate than it needs to be, as long as it's correct, you're fine. And that would be inches cubed. All right, so there you go. That's one application of differentials when you're trying to find maximum possible error. We're done with this section. Yay.